So go ahead and label 5-1, part 2, angle, bisectors, and triangles. Am I bothering you?
No, we're just talking about each other. You're also going to need scissors, glue, colored pencils. You can gather any of those materials you might want out for your notes.
Scissors, glue, colored pencils. Scissors, glue, colored pencils, and your notes. You don't need a ruler today, no. What? I'm a nice human. Alright, we're going to start off by finishing up in 30 seconds. We're going to get ready to write in 30 seconds.
Who was this guy? What did he go?
The nurse? The hospital? I don't know.
Can't give him
Alright, here we go. We're going to start off by just defining an angle bisector. And if you have a better way of describing an angle bisector to yourself, you are more than welcome to put it in your own definition. Okay? But an angle bisector is a line, or it can be a ray or a segment that cuts an angle in the middle. No, I'm good, thank you, though. I'm good. Okay, angle bisector is a line that cuts an angle in the middle, or it could be a segment or a ray.
Do you have an extra pencil?
Alright, so for example, if I have an angle bisector, that's going to cut this angle in half. So this is the bisector. And just like our warm-up, what do we know about the two smaller angles that are created then? They're congruent. And how do we show that two angles are congruent? The little arc lines. Me not too. Oh, yeah. So where? Over there? By Jackie? Yeah. That's Jackie. Okay, so we know that this is congruent. This is the same as this. So if the top was 47 degrees, what is the bottom? 47 degrees. All right. You don't need to really trim this. You can just glue this in. You're going to take this whole table that has angle bisector theorem, Converse, and in center. You're going to glue that whole thing in right in the middle. And you don't need to take time to trim it because it should just fit on your paper just fine. If you really need to trim it, do it really quick. We're going to move on real soon. Someone in the bathroom. I don't know. What do you think? I don't think so. Thanks for asking. So you're just gluing in that whole table. Don't really need to trim it too much. Glue it in as it is. I'm going to use 3 colored pencils. So I'm going to use green, red, and blue. If you want to use the same colors, you can, or you can use your own colors. That's fine too. I'm going to use green, red, and blue as we do our definitions here, and my pencil. So glue in that table. If you want to get 3 colored pencils ready to go, so you can label with me. Color code. Is there another glue? That one. Sticky. Maybe it's not sticky. It's sticky plenty. Look at this. They're crazy. It's blue. Blue is blue. You can do it. You do you. I'm just giving you a hard time, Mazda. Alright. So the first thing we have is our angle bisector theorem. And we're going to write our theorem based on what we know. And in this problem, what we know is we know that these 2 angles, okay, I lied, I'm going to use 4 colors. This angle here and this angle here are congruent. So we're going to start with that, which means if the top angle and the bottom angle are congruent, what do we know about this line? Or this ray? Yeah, it's a bisector. Okay, so to start off with, we're going to say if segment, or ray, actually, because there's only one arrow. Now, does that ray start at B and go past F, or does it start at F and go past B? It starts at B and it goes past F. So if ray BF bisects angle, you just have to push this one. Okay. What's the big angle that BF bisects? We want 3 letters for angles. DBE, or we could say, not F, we don't want that one. We want this big overall one. So we could go DBE, or we could do EBD. Yep. I'm going to stick with DBE though. Okay, I'm going to color code a little bit, so I'm going to shade in that BF with red. I'm going to make that angle DBE. Okay, so we know that there is a bisector there. What that's going to end up telling us is that the 2 distances, the 2 segments that are created based on that point F, this DF and EF, I did those in green. It's getting hard to tell. All the colors. Okay, we know that those are going to end up being congruent. Okay, so when we look at this, we know that because we have those angles that are congruent, that's what we're starting with, we then can say that those green segments, the DF is congruent to EF. Okay. All right, we're going to now do the converse. So what does converse mean? To switch it around. So what are we going to start with in the converse? If DF is congruent to EF. That's how we ended the last one. We ended it with DF is congruent to EF. So we're going to start this one with DF is congruent to EF. So we already know this is congruent to this. That's how we're starting. Then, what's our conclusion going to end up being? BF bisects angle DBE. All we did was we just took this and we just flipped it around. So because these are the same, we know that this BF bisects DBE. So to know which theorem you're using is going to just be based on what you're given. If you're given a bisector, then we're going to use that top theorem. If we're given two segments are the same, we're going to use that converse. Okay, so it's just based on what parts of the problem you know. Alright, you are going to, on this sheet of paper, you're going to cut off number 3. You can keep 1 and 2 together and glue that on the bottom of this sheet paper. Just set problem 3 aside for now. And put 1 and 2 on the bottom. Johan is so lonely. So lonely. Did you go bring it to him? How are you the nicest human? So we're just going to take 1 and 2. So you can just cut off 3. Yeah, I'm going to keep 1 and 2 together. I just glued 1 and 2 together in. So just 3 can get cut off. If you have 1 and 2 apart, that's fine. Just glue them in together. They're next to each other. Yeah. And then we'll use that in a second, though, so don't get rid of it. Set it aside. So when we get geometry problems, what's really important is that we're able to tell what parts we are given based on that diagram. What does it tell us? What information do we not even have to think about? Okay, well, we have to think about what we don't have to think about. It's kind of confusing. Okay, so in that first problem, what are we given? What is some information that they tell us? Yeah, AD bisects what? So if I look at AD, how did I know that that bisected something? Because it told us they were congruent. They had these little teeny tiny arcs there. That tells us that it's congruent. What's the angle that it's bisecting? What? BAC. Okay, so that's one piece of information we're giving. Good. CD equals 5. Okay, it doesn't tell us 5 what, so we can always write 5 units, and that just tells us if we decide it's feet, we would put in feet. If it's centimeters, we put in centimeters. Okay, so because we know it's a bisector, we know those angles at that vertex are congruent. What does that tell us about the segments at the end of that angle? What do I know about the CD? Yeah, CD is congruent to BD. Which then means if I'm trying to find DB, how long is DB? What? Yeah, 5 units. Or 5. So number 2, we're not going to write down everything we're given. We're just going to note it for our brains. In number 2, what do we see that we are given? Say it again. WY bisects XYZ? Okay. Do we know that it bisects it right away, though? Does it tell us that this is 28 and this is 28? No, but what does it tell us right away? Which parts are the same? XW is the same as WZ. We have those are congruent. So because those are congruent, we know that this does end up being a bisector. So we're going backwards. This is that converse. We started with the sides are congruent, which means that that angle bisects it. Okay? Which means that these are congruent. I think there's a line right now, dear. Can you ask Miss Sider? She knows kind of the order. If you ask Miss Sider, I think she might know the order. Oh, you don't? Is it just Damien? Okay, Hakeem is gone right now. Yeah, I think. IDK. Okay, so since these are the same, that means these angles are the same. So if this top is 28, what's the bottom? 28. Now let's see what it's asking us to find. It's asking us to find XYZ. So what angle is XYZ? If I trace that, XYZ, is it the top angle, the bottom angle, or the whole angle? The whole angle. So how am I going to find the angle of the whole thing? We add it together. And what is 28 plus 28? 56. Whoops. Okay, so it's kind of confusing. It seems pretty intuitive. The reason why it's confusing is because it's like easy. Sometimes when geometry becomes easy, it becomes confusing. Okay, really what this is saying is if these are the same, then these are the same. Okay, or vice versa. If these are the same, then those are the same. Okay, it's really just showing us that based on that picture, if we know one of those things, we can say the other thing. Okay? All right, we are going to go back up to your table. And we're going to fill in the in-center. So for the in-center, Damien. Alright, for the in-center, what we're going to be starting off with is the whole triangle. So the whole triangle here is ABC. Okay? That whole triangle is ABC. DC. DC. Do you have your notes? DC. Do you have your notes? Do you have your notes? Okay.
For right now, really this kind of in the middle of your page, and then okay?
All right. So, in that triangle, ABC, point P is made from the angle bisectors. So what they did is they looked at each of these angles and they cut each angle in the triangle in half. Okay, they cut each of the angles in the triangle in half. So what's one of the angles in the triangle? Angle B. What'd you say? B? Did you say B? D? Angle D. Angle D is on the side. That's not an angle. That's part of the side, though. So angle C is a corner. So really we're looking at the corners of the triangle. So it's going to take this side and we cut that angle in half. And we see that because there's three lines. What other angle are we cut in half? Angle A and angle B. So those are angle bisectors. But what's really cool about this is that when we have that angle bisector to create that in-center, is that in-center ends up being in the middle. Okay? And remember we have 4 different centers we're talking about. Yesterday we learned about the circumcenter. Today we're learning about in-center. Tomorrow I think we learned about the orthocenter. And then the next day we learn about the centroid. Okay? They're all different ways of saying the middle of the triangle, but they're all a little bit different. This time, the middle of this triangle means it's the same distance between that point and the sides. So if I started at point P, and this was a room, and I had to walk to each wall, each of these distances from P to E would be the same as P to D, which is the same as P to F. Okay, so P to E is the same as P to F, which is the same as P to D. And that's probably going to be one of the more important things about the in-center that you need to know. The 2 really important things is the angle bisectors, and that those 3 distances end up being equal. So P is in the center. If I wanted to stand in one point and have it be the same distance from me to the wall. Okay, and that's different for a triangle than when it is like a square. If we're talking about this room, I'm in the middle of this room. If I want to walk to this side, it's the same as this side, same as this side, same as this side. Okay. Alright. I'm going to flip over to the next page and glue in problem 3 on the back. So go ahead and flip to the next page, glue in problem 3. Even if you have room on this page, you're probably going to want to go to the next page. So this one's kind of a lot of work. Okay. So glue in that next page, problem 3. Okay, so in this problem, we know S is the in-center of triangle MNP. We're actually going to have two problems that stem from this. We're going to do two types of problems from this problem. The first problem, we're going to find one of the angles. Okay? So our first direction is to find the measure of angle SPU. It should be on the... You get the big thing? No. Alright, so if I look at the total triangle, what's the big triangle we're looking at? MNP. And I know that each of these lines coming out of the angles are bisectors. So if this bottom one is 31 degrees, what's this top one? 31 degrees. If this side is 28, what's this side? 28. Okay, and if I think about that triangle, I'm just going to draw it over here without all the lines in the middle because that looks like craziness. If I have M and P, how many degrees is angle M going to end up being together? It's 31 and 31. 62. How many degrees is N going to be? It's 28 and 28. $56. So how can I find that missing angle? Angle P. Good. We know all three angles in a triangle add up to 180. So however you do that, you do it your way. So some people like to add them and then subtract from 180. Some people like to do 180 minus 56 minus 62. That's the way I like to do it. So that's what I'm going to write. 180 minus 56 minus 62. If you want to add 56 and 62 together, you can. (56 minus 62), and I get 62. So I know that this angle P is 62 degrees, so it ends up being an isosceles triangle because two angles are the same. But the question was find SPU. So if we take a look at SPU, I'm going to start at S, I go to P, and then up to U. Is that going to be the whole 62 degrees? No. So how am I going to take 62 degrees and I need to cut it in half? Divide by 2. And what's 62 divided by 2? 31. So for our final answer, the measure of angle SPU equals 31 degrees. So for this problem, we really ignored quite a bit of the information, other than we knew that it bisected it. So we were able to say 31, 31, 28, 28. And then we were able to use that information to find that last missing angle and split it into 2. How are we doing? Is this madness? It is. I don't know what to tell you other than it is madness. Why do you need to learn this? I don't know. Somebody Google it and figure it out for us. Thanks. Miss Sider can do that. Miss Sider, why do we need to know this?
Because we're going
Okay. There probably are. It's just good for us to think about triangles and relationships in general. All right, before we do our next part, we're going to think about the Pythagorean Theorem just for a moment. So we're just going to make a little side note about the Pythagorean Theorem.
Does anyone remember that? Do you remember hearing that or learning that? What does it deal with?
Pythagoras. Do you guys want to know about a bunch of drama? Pythagoras actually didn't invent the Pythagorean Theorem. It was one of his students that invented it, but then Pythagoras was the one that brought it to the official math people and was like, look at this theorem we made. And then they're like, oh, Pythagoras, you're a genius. And they named it after him, but it wasn't actually Pythagoras that made it. What? A guy way back in ancient Greece.
Like hundreds and hundreds and hundreds of
BC.
years.
Anyways, Pythagorean theorem looks like a squared plus b squared equals c squared. It's on the front of your notebook. Fun fact. Okay, and it deals with a right triangle. And the big thing with a right triangle when we do this, the most important part about the Pythagorean theorem is the c. The c has to be across from the 90-degree angle. Okay, so wherever a 90-degree angle is, whatever's across from it, that has to be c. That's the hypotenuse.
So if you haven't done a ton with the Pythagorean theorem before, what I would do is write yourself a little note that maybe just say, highlight that C and say across from 90 degrees.
Okay. All right, what our next goal is going to be is, based on that picture, we are going to find SR. Based on our picture. I'm going to show more work down here, but for just a second, we're going to scooch back up to our picture. Okay, so if we go back up to our picture, where is SR? It's like from the middle to the bottom, right? And with the in-center, we know that there's 3 segments that are congruent to each other. What other segments are congruent? SR is actually going to be congruent to SU, and it's going to be congruent to ST. Do they look the same? No, I got this from the textbook. You'd think that the textbook would have a good picture, but the textbook tricked you. They're the same, even though they don't look like it. They're congruent. So what we're going to do is we're going to look for the side lengths that we know, because we're going to look for SR. What side lengths do we know already? What's SP? 10. Do we know RP? No. So this SR is going to be really hard to find without that RP. So instead of using this one, let's try and find one of these 2. So using this 10, what other length do we know? We know TS? This one? Not quite. We know UP. UP is 8. And that's a right triangle, so we can find this SU. And we know once we find SU, that's the same as SR. Okay? So what we're going to do, it's going to be kind of confusing, I know. But you're going to stick with me, because we got this. We're rock stars. Okay? Down here, we're going to say SR is the same as SU. And I'm going to try and copy down that triangle. So that triangle looks kind of like this. The 90-degree angle is here. So it's like I cut it out of that big triangle, and I'm pasting it down. That SUP. Okay, and what is S to P? S to P is 10, and U to P is 8. So our goal is if we can find SU, we know that that's going to be the same as SR. So we're just going to find a missing length in the triangle. And to do that, we're going to use our handy-dandy Pythagorean Theorem. Okay? So, we're going to do a squared plus b squared equals c squared. Which one is the most important that we need to know for sure it goes into place? A, B, or C? C. And C is across from the 90-degree angle. So C going to be 8, 10, or the missing part? Good, the 10, because it's across from the 90. So this is going to equal 10 squared. Now between the A and the B, it doesn't matter which one is the 8 and which one is SU. Which one do you want to be 8? A or B? Okay, A. So 8 squared plus, and we don't know this part, so we're going to leave that as SU squared. What does it mean to have something squared? Not times 2, multiplied by itself. So what is 8 times 8? 64. What is 10 times 10? 100. And then we're going to solve that. We're going to try and find SU, the value of SU, because we know that's the same as SR. So what am I going to get rid of first, the 64 or the squared? 64. How do I get rid of adding 64? Minus, good, both sides. So SU squared equals 36. So I want to think of a number that times itself, a number squared, that is going to give me 36. What times itself is 36? You got it, Johan. Give me 1 second, though. 6 times 6, yep. Wanted to give people a little bit more time. So if SU is 6, what is SR? 6, because they're the same. Holy cow, that was a lot of notes. Who made us do all those notes? They're the worst. Yeah, it was me. You're right.